So our next lecture is about efficiency. So not only are we just talking about energy itself, but now we're going to add in the concept of whether we are using energy, transferring energy from a form, from one form to another efficiently. So this first slide talks about incandescent light bulbs, and it says that we have billions of them illuminating Earth at night. But are these light bulbs actually efficient? Nowadays, we've kind of moved away from incandescent light bulbs. Those were the old bulb light bulbs. They were not as efficient. They actually only provided about 5% of the light radiant energy that we needed, that we wanted. But if you ever touch those bulbs, you notice they got very hot, and that's the thermal output was actually about 95%. So the efficiency of a light bulb, an incandescent light bulb, was said to be 5%. Not a very good statistic. So that's why we've tended to phase them out to different light sources like LED or other types you might have seen, like halogen bulbs. But how do we calculate efficiency? Well, it's a simple equation. It's the output energy divided by the input energy. And it's important to note that there is no 100% efficient device or process. There's always going to be some type of waste energy. Thermal energy is the most common type of waste energy, unless it's the energy we are trying to get out of the system. So this actually brings us to a different idea of the most energy efficient system we could have. So a system with 100% efficiency would be a perpetual motion machine. It would be a machine that would continue to move forever without, after an initial input of energy, it would never need more energy to keep moving. So really, it would have 100% efficiency or greater than 100% efficiency. And this concept has been around for many years. Based on our laws of thermodynamics, it is impossible, but it's a nice kind of thing to think about, this perpetual motion machine idea. So here's a slide to copy down about efficiency. It's the ratio of the output energy and the input energy. The input energy is always greater than the output energy, and they're both measured in joules, so efficiency itself is a percentage measurement. Let's do a quick little efficiency calculation. Here we have a firefly, and this firefly is emitting radiant light, and it uses some chemical energy to do that. Well, it says here the firefly uses 4.13 joules of energy, of chemical energy, to produce 6.36 joules of radiant energy. So what is the efficiency? We do 3.63 divided by 4.13, and we have 87.9% in terms of efficiency. We could look at efficiency for systems as well. So this is a painter. He's trying to raise a paint bucket using a pulley system. Well, the energy that he uses is 1.93 kilojoules of mechanical energy. So the first question is, how much work is done? Well, the work is equivalent to the energy that was expelled, so it's 1.93 kilojoules of work. But what is the energy of the paint can at the top of the 7.5 meter distance? Well, in that case, it is 7.5 times 20, because that's the mass of the paint can, times 9.8. So we have 1.47 kilojoules. So now we know that the energy that we have out is 1.47 kilojoules. The energy in was 1.93. So what's the efficiency of the system? We take that 1.47 divide by 1.930, sorry, 1930 because it's not written as a decimal, and we get 76.2 in this case, because we should report this to 3 significant digits. So a primary goal of scientists and engineers is to improve the efficiency of devices and processes. Light bulbs are more efficient when they transform a greater amount of electrical energy into radiant energy. So we've achieved this using fluorescent lamps or compact fluorescent lamps, CFLs. Now actually LED light bulbs are more seem to be a bit more common, and they are more energy efficient. Fluorescent lamps transform up to 25 of the supplied electrical energy into radiant energy, which is a significant improvement in efficiency. They have some problems though. They cost more to produce, and they contain mercury, which is a poisonous element and causes pollution. So LEDs are actually a bit better than those CFLs, which were quite popular for some time. So where do we get energy from? Well, the energy makeup of each kind of jurisdiction in the world is a little bit different. I believe here, I think this is the energy in Ontario. Actually, I don't think that's right. It's not. But this is this pie chart gives you some output, some types of energy sources: nuclear power, coal, natural gas, hydropower, and oil, and then it says some other. But any energy resource is an energy-rich substance. And of those types of energy resources, we have renewable and non-renewable, where non-renewable resources are ones that they're not readily recreated. Things like oil and natural gas and coal. Nuclear energy is considered non-renewable because it takes finding nuclear fuel is a bit more difficult, so that is an issue. And then we have renewable energy sources. These are substances with an unlimited or a supply that is replenished easily. Hydroelectricity is one. Solar, wind, tidal, geothermal, biomass, and fusion energy are others. So although renewable energy resources are replaceable or unlimited in supply, non-renewable energy resources such as coal, oil, and natural gas continue to be the most widely used. So what are some reasons? Well, we have to work off the pace of technology, and the technology to transform fossil fuel energy into other forms of energy is well established, and it's easier, cheaper, and there's more knowledge base to produce energy using fossil fuels than it is to produce renewable energy from renewable sources. We also with renewable sources, it might take a lot more. May take a lot of area to get something to have a energy transformed. So, for example, solar energy, we might need a lot of solar panels to gain as much solar energy as we need to close off a nuclear, or sorry, a coal-fired power plant. Windmills take up space as well. You can't have all the windmills next to each other, so you have a wind farm or a windmill farm. So those are some things to consider as well. Here we have a little chart for this question. It says the three main sources of electrical energy in production in Ontario are fossil fuel, nuclear energy, and hydroelectric. Complete a chart similar to the one below detailing the type of energy, how much electrical energy is produced by each, and some advantages and disadvantages of each. So that's something you can do on your own. I don't want to use up the time in this lecture to do that, but it would be it would be worth completing this practice question because you might see something like this on a future assessment. Fossil fuels are recovered from the ground in raw form. Then they undergo some form of energy transformation to make them useful. When burned directly, the fuel products can be used to operate the engines of vehicles and furnaces to heat buildings. But as the supply of oil and natural gas diminishes, less conventional fossil fuel resources such as Western Canada's tar sands will become more important. So here you see an excavator grabbing sand, or what we call the tar sands from Alberta. It's basically sand that is saturated with oil. So getting the oil off the sand is important, and then we can use that as another energy source. So how do we use these sources of energy? Generally, this is the same process you see for all different types of energy. But for fossil fuels particularly, where we have to burn the fuel, this is how the process will work. So first, we have to understand a little bit about what is an electric generator. And we are going to study that in our next unit. But the general idea behind an electric generator is if we can have some magnets moving, we can generate some electricity. So we need something to move those magnets, and to do that, we basically need an energy source to turn a turbine. So here in this image, we have fossil fuels being burned. They are heating water, and the water becomes steam. The steam from the water turns a turbine. That turning turbine ends up turning magnetic coils inside of a generator. That generator then is able to generate electricity. The water then condenses, or the steam condenses into water, and it's sent back to the system to be burned by the fuel again to turn back into steam. So that is an example of how we would use certain fossil fuels, or lots of fossil fuels. Basically, we burn them. The thermal energy is used to turn water into steam, which is then used to turn a turbine. So about 36% of Ontario's energy comes from fossil fuels. Nuclear energy is a form of potential energy that is used for its generation of electricity as well. With nuclear energy, the main isotope or the main element we use is uranium. Uranium comes in a number of different isotopes, and it tends to be not as stable in certain isotopes. What happens with uranium is if it can be hit really hard with a neutron, it'll actually split into other elements, and that split is called nuclear fusion. So when the uranium atom is split, it becomes two other elements, and it releases a lot of energy. And that energy is released mainly as heat. That heat is used to heat water, and then we use the process we saw up here to heat coils. Coils heat the water, turn it to steam. The steam turns the turbine. The turbine turns the magnets. The magnets generate the electricity, and then we use the electricity for whatever purpose we need for it. The water condenses and then goes back to be burned again, or to be turned into steam again. This is one type of nuclear energy. There is another type, and that is nuclear fusion. That's the energy source that we have in the sun. That's where we put smaller elements close together, and they fuse into become another larger element. So I guess this is nuclear. It's generally the same idea. So we have a pool of water. The reactor core heats up the water, and that ends up making the water turn into steam. That steam turns the turbine. Same process. It's just a little bit different in terms of how we get that energy to burn. So about 37% of Ontario's energy comes from nuclear energy, and it's out of the Pickering Power Plant in Pickering, Ontario. Hydroelectricity is another type of energy. This is an energy source that uses the kinetic energy of rushing water to turn turbines directly, and that turning of the turbines is then used to turn the magnets, which generate the electricity. Often, this used to be Ontario's #1 source of electricity generation, so a lot of our energy is called hydro because of that. Generally, I just kind of said what happens, but we have any time where there's a change in elevation of a river or like a water source, we can create a dam, which will then let in some water at a time through the dam, and as it does that, that water would turn a turbine, which can generate the electricity we need. And about 26% of Ontario's energy comes from hydroelectric generating stations. So here's the answers to that question previously. I mentioned that you could do it yourself, but we've kind of done it here. So fossil fuel is non-renewable, nuclear is non-renewable, hydroelectric is renewable. But there are some cons to consider. So with hydroelectric, it actually is harmful to both land and water aquatic habitats. So that's something to consider as well. There is some environmental damage with hydroelectric. For nuclear, the emissions with nuclear energy are actually just water. It's just steam. So it's actually a very clean source of energy. The problem is the waste of the nuclear energy. So when those uranium atoms split, they create other radioactive elements which are we don't have much of a use for. So they need to be stored, and when they're stored, if they get out, they can cause there's radiation disasters that could happen, right? So that is the issue with nuclear. Although Canada is pretty safe with nuclear energy, so hasn't been an issue. There is still a lot of potential for that people have a lot of concern for, so that's something else to consider with nuclear. Fossil fuels are cheap and easy, but they are big polluters, so that is their big disadvantage. They also increase the amount of carbon in our atmosphere, which leads to global warming as well. So one fact is certain in Ontario: we are going to need to generate increasing amounts of electrical energy far into this foreseeable future. Our population and economy are growing, which means that we need more electricity. However, none of the renewable energy sources can currently be manufactured and operated cheaply enough to make them a viable alternative in the foreseeable future. So the logical conclusion then is that we have to build new generating stations that use the same non-renewable energy sources as our existing generating stations. However, we should also try to reduce our energy output. So we need to conserve energy. Some ways you can conserve energy: turning off lights, turning off electrical devices when you're not using them, not using as much water, not using dishwashers and clothes washers as much, or using them only when they're full, and using public transit and carpooling instead of driving around with your car as much. So those are some things to consider as well. It says here, an article on the internet claims fossil fuels are actually a renewable energy resource, since decaying plant and animal matter is making new oil, natural gas, and coal all the time. So let's discuss the validity of this. It says this is true in the sense that they do come from decaying plant and animal matter. However, they're not renewable in the sense that it takes millions of years for that to happen. So I guess you could say that they are renewable sources, but based on our lifetime, they are not renewable.